to Thomas. So Thomas, you're back on stage. So now it's your turn to share with us how geospatial modeling links to the general indicator modeling framework for decision support. So yes. Please, Thomas.
Okay, thank you very much. So I would like to take up the idea of doing standards together. And especially there was also the topic already today of how to crack the silos, the information silos, how to connect information. And I think this kind of a concept that we have developed over the recent years at our chair may be something that could be also interesting for ISO. Maybe also, I don't know, it could be considered in the future as a standardization activity. At the moment, I don't have a dedicated plan because I also don't have a dedicated financing for going in such a way. But let's see. It's joint work by Mostafa El Foli and Tatjana Kutzner. Both are also online. And it's mostly also really the PhD work of Mostafa. And so, however, I took the opportunity today to give this presentation. And so, what is it about? I mean, in smart cities or in general, if you are using GIS data for specific decision support, may it be in the energy domain. So you want to know which buildings are suitable for retrofitting, or if you think about traffic planning, or transportation planning, then where to put a road, which road should be closed. So in order to change then the flow of traffic inside the city, it all comes in the end basically to measuring landscape and city performance. And I'm not just talking about measuring indicators on the level of the entire city. No, the energy demand of a single building is of course already an indicator. Of course, you can aggregate those indicators then to a level on the district levels. You can say, okay, for the entire city quarter, we have that amount of heat energy demand. And at the same time, you can also think about what is the solar energy that can be generated and maybe also that is currently being generated for a certain district. And again, these are indicators. However, they are always related to geospatial objects in this case, the building. If you think about what's the average driving speed inside a piece of road or inside a section, then within a section, then again, this is an indicator which can be associated with the piece of road. So again, we are interested in having basically different kinds of indicators which are from completely different domains. And so you see, we have ecological indicators, we have financial indicators, social indicators, etc. And all of them are related somehow to the landscape or to the city and its parts. And typically, when you have very important indicators, people are talking about key performance indicators. And you already mentioned this today. I think ISO TC 268 has also these smart city indicators, which is, I think, 37120 or something, that ISO standard, which is also defining indicators to measure the performance, the smart city performance of cities. The question is now how to compute those things. And on the one side, you can see we have these kind of indicators on the left side. So you see we have energy indicators, mobility, etc. And then on the other side, we have existing data. And data which comes from completely different organizations and which also come in different data models. And so, for example, what you see here is everybody of you is probably familiar with Inspire. That's the European data modeling and the European spatial data infrastructure, which includes a set of data models. Then also we have, this is just an example from Germany, ALKIS and ATKIS. This is the German cadastral standard and the German topographic data modeling standard. But of course, other countries, UK has Ordnance Survey, MasterMap, and others have similar data models. Often they are nowadays modeled based on ISO TC 211 standards. And of course, there's also CityGML data, which is representing 3D, semantic 3D city models. And finally, BIM data also. So we have very detailed representations of the built objects. And now the question is, how are these related? And observations that you can do is geo-based data are typically available for entire countries, or at least for entire cities, and they can be used to compute these indicator values. Often, however, you need additional domain-specific data. So some information, for example, if you want to determine the energy demand of a building, you need at least have some information about the construction type of the building, and often the age of the building or the age class is being a good indicator to be used to derive, for example, insulation values for materials from that. So these kind of information may not be included in all city models worldwide. So you may need some additional information. However, all these geospatial information that I've mentioned before are based on standardized semantic data models, or sometimes you can also call them ontologies. And so far, the indicators, however, they are typically not formally modeled using a standardized framework. And also no systematic model exists yet to link indicators and these kind of geodata or geo-based data. And that is basically addressed by this framework, which I would shortly like to present. The entire framework is based on the idea of model-driven engineering, which is, I think, of course, also the underlying principle that is being used here in the ISO TC 211. And basically, MDE puts the model in the form of formal specifications in the center of software analysis and design. And application relevant structures are represented by formal data models, for example, using UML. And MDA, which is also being used in ISO TC 211, is considered being a part of MDE. And the idea is, of course, to, as far as you can go, derive automatically other models or also program code from this kind of model-based representations. However, there's an important thing in MDE that is not so much addressed in others, for example, in model-driven architecture, is the linking of different models. When people today talk about linking of different models, they often talk about ontologies. And they say you need to use an ontology. No, you can also use MDE from the domain of data modeling. And so you can also use UML, and you can also use all the representations that are very common to everybody here in TC 211. And this is then called model weaving. And so different models are then linked by what is called a weaving model, which takes care of data transformation across the models. And now to sketch the idea is to say, okay, let's assume we have the different levels of modeling. For example, in geospatial information modeling, like is supported by ISO 1909 and also the national data models that are being used, you can see they are residing on different levels of this MDA hierarchy. And you can say, okay, in the lowest level, let's assume we are looking at CityGML as a specific application schema. Then on the lowest level, M0, on the instance level, we have the objects of a specific city model. For example, the buildings of Berlin. So these are the instances, and they all are modeled according to that data model here. And that's basically CityGML. And CityGML defines the structures of all possible 3D city models. So CityGML is being used not only in Berlin, but also in Singapore, in Tokyo, in Hong Kong, and in Rotterdam, Zurich, etc. So in many, many cities around the world. And however, that data model, again, follows a certain principle, and that is being defined here with a general feature model. So the interesting part is that, for example, the Inspire data models, they would be, you could say, brothers or sisters to CityGML, and the national mapping agency data models like OS MasterMap is also a brother of CityGML because all of them are modeled according to the general feature model. Okay, and also LADM would also maybe belong to that. Now, let's extend this to indicators. Why, when we have geospatial data models, why don't we have a similar framework for indicators? That's the question. And here's an idea to say, okay, I may have an indicator, a key performance indicator A for building Y. That could be, for example, the heating energy demand of that building. And that is an indicator that is very specific and tightly coupled to this object. And then, however, that indicator also needs to be modeled somehow. So we need a framework or a data model to represent it. And our suggestion is to have here, similar to application schemas for geodata, also application schemas for indicators. So you can then say, okay, let's model the indicator here separately from the geospatial model. And then we can also have other application schemas. So we may have energy-related application schemas, we may have climate-related application schemas, we may have traffic-related, etc., etc. And then also these objects on the bottom level are linked to these indicators. And then, of course, we need, similar to ISO 1909, we would also then need a concept that would be called general indicator model. And these schemas would then be an instance of this one. As like CDGML is an instance of the general feature model, then an energy-related application schema could be an instance of this one. And there is, of course, then the linking. And here you can already see what I mean with breaking up the silos, because this is now really linking data from different domains and different application contexts to existing geospatial data models, not just CDGML. This is just an example here. And so there are then requirements for this indicator model. First of all, you need to be able to support different kinds of indicators. We have numerical, textual, categorical indicators, etc. Then we can also think about, we have complex indicators that can be composed and computed from attribute values from associated city and landscape model objects. We need to be able to express constants and mathematical expressions. And of course, we also have indicator value aggregation, like summation, average, maximum of other indicators. So for example, the heating energy demand for a district consists of the heating energy demand for all individual objects in that district. So, and that can be also expressed using UML. And what we can also do is we augment indicator values, or what we can do is we can augment indicator values with meta information, like accuracy, lineage, source, etc. So, and if you would be able to model for each individual indicator value, also the accuracy, you can then also include sensitivity analysis along the processing chain of the computation of the indicator. So it can really lead back to the original data sources and the original data items and say, okay, what's the provenience of that specific indicator value? And so that's also a chance here. Let's give you an example. And of course, I have to use a bit of UML, but it will not be coming too difficult, I promise. So what you see on the one side is, now let's assume you're an energy planner and you want to talk about heating energy demands in cities, because that's an important topic also for smart cities, for example. Then, of course, you have an idea about your indicators you're interested in. You probably don't have an idea about Inspire data models, about CDGML, about OS master map, or about the German national models, etc. So first of all, you're interested in your own representation. And then let's assume we have something that is called heat demand, or heat energy demand. And then you can already see, we can say, okay, that's a subclass of a numeric indicator. And here, every indicator has a value. And so this will be inherited. So the heat demand would have this attribute value. And then, however, heat demand for itself does not make sense, because the heat demand is always the question, heat demand of what? The heat demand of my car, the heat demand of my building, or whatever. So these kind of indicators typically only make sense when they refer to some reference. And often the reference is an object, a geospatial object. And that's basically expressed here. So we have further sections now in our schema and say, okay, we now have to create object-related domain indicators and say, okay, we have something like the district heat energy demand. That's interesting for the energy planner or for the urban planner. And then, however, we also have the building heat energy demand. And both of them are subclasses of a heat demand. However, they are a little bit more specific because they also need to relate to a reference object. And here you can already see, here we have now an interface. And that's basically the interface to our other existing geospatial standards. However, that kind of systematic approach, first of all, it would allow that the energy planner can create such a model without thinking about whether in CDGML buildings are modeled in that way or in this way, or whether to use IFC and for BIM and having the specific modelings there. So it's really the idea of separating these concerns. So that model is completely defined purely from the logic and perspective of the energy planner. And then, however, so you can see many of the reference objects in the context of urban and landscape indicators, they are spatial objects. And then we can see, okay, let's have a look at an existing geospatial information model or geospatial application schema. CDGML is just an example here. It could also be OS master map, or it could also be some Inspire data model. And now the point is actually you have here the existing data model, and that's the domain of the geodata provider and also of ISO TC 211, for example. And then, however, you need to see how difficult it will be to connect the reference objects that are required here with existing feature classes and feature objects of that data model. And in this case, for example, you have what is called a building connector, which simply connects the class building from CDGML with a building that is required here as the reference object. And then in CDGML, we don't have a class called district. However, what we have is the class called city object group. And that is also used to model, for example, urban districts. And or it can also be modeled to model the entire city or group everything inside the city. So what we made is now the connection here to this connector. And now you have a complete chain. And the idea is then adding OCL rules here at two places. One place here at the connector and one place here at the object-related domain indicators. And in these OCL rules, we embed the computation rules and say, okay, that value here, the volume, is taken from that model by applying the volume calculation on the 3D solid. And here, however, the energy demand in the end is being computed by taking into account the building volume, maybe also the building H class, etc., etc. And then, however, this is being expressed as OCL on this side here. And this is further explained a bit. So using what object constraint language is being used. So you see here, the building heat energy demand is, for example, let's assume we say, the building heat energy demand can be computed by taking the volume multiplied by 0.97. This is a fake formula. Of course, we did already this with real, also other ISO standards for energy demand computation, and the models are really huge. But of course, it was possible, and we can show it. And we did a master thesis showing how these other standards for computing building energy demands can be mapped onto this schema. And then, for example, for the district heat energy demand, you can simply say, okay, summing up, it's basically the value is simply summing up the heat demands of the instances that exist here. So, and second OCL rule is at the weaving class, because we have to provide building objects here. And so we need to provide a rule here, which simply says, okay, there need to be a building object here, and there is one object here. And however, in order to set this volume here, we can take the volume that is here as associated from the building data in CDGML, or we can call a function to compute the volume, maybe from the associated solid. That's also a possibility. So let's quickly summarize that. Each indicator application model is defined purely from the viewpoint and requirements of the domain specialist, because what we don't want is that the domain specialist have to learn in the first place how a specific data model, CDGML, IFC, or something looks like, because then sometimes people make suboptimal decisions how to model their indicators. And so it's just modeled from their perspective without taking into account any geospatial data model. And then the data model is separated into 5 consecutive sections. You have the abstract indicator classes, the domain-specific indicators, object-related domain-specific indicators, and the reference objects. And the 5th section, it addresses the linking of the indicator model with a geospatial application schema, like CDGML or Inspire. And the weaving classes relate reference objects with feature types from the geospatial application schema. And this is, again, the diagram that you've seen before, and here are those 5 sections. And you can really create this in a systematic way, and I can also show you an example in a minute. This is now I won't explain that in too much detail, but this is basically the meta model for the general indicator model. And this is, you can say, the analog data model as is given for ISO 1909. ISO 1909 is the general feature model, and which also has a UML diagram. And this is exactly the similar thing for the meta model. And also here you can see basically these sections which I have shown before, where you can find them. Here are the concepts which are defined here. So that's the That's the meta model. What can you do with this? I mean, one thing is you can say, okay, I can really say for the domain stakeholder, please try to represent your indicators in a standardized way. Standardized means use UML, use OCL to express computation rules, and do that kind of 5 sections, or at least in the beginning 4 sections of the modeling. And then, however, you can check what data set and what data model out there in the free world or in the wild world is probably easiest and most powerful or rich to connect here, which can probably provide all the data that is being required here, because the rest is all derived from here. So that means you really have to check for the coherence of these 2 data models. But this framework also allows to assess this. We can find out how many one-to-one object mappings can we find. For how many cases we have a more difficult situation like 1 to n, or in the most difficult cases, n to m. So n objects here representing m objects here, which is a bit of a problem then. But then, of course, you can also do the weaving to inspire data models. And you can also do the weaving with BIM and IFC, for example. And then you can really assess for which one, maybe also, first of all, is data already there? Is there already a city model and CityGML? Maybe there is no data in Inspire, so that could be done this way. Or if you really say, okay, we need data to compute this, but which is probably the best data model in which my data should be coming, my spatial data should be coming and be related here. So where's the pain? Where's the least weaving pain, I would say? And so we can analyze and compare how good and easy an indicator model fits to a specific geospatial application model. And this, I don't expect that you can read this, because there is a link here at the bottom to a paper that was written by Mostafa and Foley and Anna Lawecki from TU Delft, who jointly worked on using this framework to see how parts of the US standard HASUS, which is basically a framework for hazard assessment and hazard analysis, being mapped. And what is shown here is the modeling of flood damage assessment for buildings. So if buildings are being flooded, there are also computation rules defined in this HASUS framework, also how the American government computes costs and how insurance companies can compute compensation costs for building owners. And this was able to be completely mapped on this framework. And the different colors show the different sections. And this is on the left side CityGML. And it was also shown how this could be created in a complete chain, and then also how programs could be derived, which then basically on the basis of CityGML data plus some extended data can really lead to full computation of all the indicators. So that's basically the step here. And then this is a slide I added just a couple of minutes ago. You see this hand drawing, and of course you can think about cracking data silos by connecting domain data, for example, using CityGML. You have the CityGML data model, and then you have a weaving model, maybe to some real estate management and value assessment indicator model. You have urban planning indicator models. You have energy demand estimation models, traffic simulation, etc. And what I can tell you is all of the examples I'm giving here have been implemented already. So this is not just future work or something. This is already has been achieved in the past. And also CityGML has a mechanism that is called application domain extension, ADE, which then basically would allow to even map this kind of extension as an extension to the CityGML core model. But as I said, the entire general indicator model framework is not specifically to CityGML. It also can be applied to all the other data models. However, just here to show this is basically taking up this, and here is basically to show, okay, the city model can be a very good integration point for all these different kinds of use cases and applications. And how is it done? Just here an example. You have a building model, for example, and then you have information about energy, about noise emission, about economy, etc. And all of this is related to the very same real world object. And this is not just a graphical or geometrical representation, it is a semantic object and represented as a building. And you don't need BIM for that purpose. So BIM is overkill in this case, especially when you go for an entire city represented like that. Okay, so, and again, yeah, if you have a city model like that, you can map the city as a specific time point, and then of course you can compute all the different kinds of indicators, and by using simulations and calculation tools. And then of course you can also virtually carry out planned actions, change the city model, and rerun all the simulations to see how this will affect it. Okay, coming back, final slide. So the general indicator model is a new framework. In fact, it's from the time perspective, it's not so new because we have been working on that now for a couple of years, but still we are currently finishing a publication on that, which needs to be published. And we have indicators for different domains in a standardized and interoperable way using UML and OCL. So that means we are using the same language as ISO TC 211 also uses. No need for OWL or for other external further standards in this case. You can link these models to the geo-based data using model weaving, and it facilitates the systematic analysis of indicators, the relationships to digital landscape city models, but also to BIM. And yeah, we can explain key performance indicators represented by 3D models. And I think that should be enough.
Thank you. Thank you very much, Thomas, for your presentation. I liked it very much because you modeled a very quick solution for cracking the silences actually during the presentation. I've seen that also Tatiana and Mustafa are here, so your co-authors, maybe they would like to complement something, to add something. I don't know, Tatiana, Mustafa.
I mean, I don't know. Can you hear me?
Yes, so I think
Yes.
Thomas gave already a great presentation and included the most important aspects already.
Maybe they can, if there are questions, they can answer on the question.
Yes, so you will see that there are some questions, some comments already. One by Peter. I think, Peter, would you like to extend your question?
Yes, so I was asking, there's an ISO IEC standard called, exactly what it's called, but it is effectively a top level indicator ontology. So a data model which seems quite similar to your general information model, but modeled in OWL rather than UML. It's similar, not so much in content perhaps, but in intent. And I just wondered whether you or your PhD student has looked at all. So it's ISO IEC 21972. It's emerged out of work done at the University of Toronto. The editor was a professor there.
Actually, maybe I don't know. Tatiana or Mustafa, do you want to answer?
So I saw that it's a quite new standard. It's from 2020. And the work we did, so we started a few years ago. And so back then, the standard was not yet available. So I think we should look at it. And I think it was in the comment that it might be similar to the domain indicator model. So it could be a good example then for the domain indicator model.
Yeah, exactly. I mean, I think it was the same. It was in 2020, and we started working actually in 2014 or 2015 on the topic already. But it would be something good to look at as well, that we refer to and check what they have developed as well.
So the standard was published then, so obviously the public draft was 2019, but the actual research work in Toronto was published in about 2014, 2015. And anyway, it's just raised that as a thing that might be worth looking at.
Mm-hmm.
Thank you, Peter. So I think there was another comment / question by Robert from New Zealand.
Yes, I was just wondering whether there were parallels between the indicator work and the O&M standard and approach and the other data models that have arisen out of that in OGC and TC211.
I'm not sure if I understood correctly the question. Could you please repeat?
In OGC and TC211, there is an observation and measurement standard,
Yes.
19156.
Yeah.
And I wondered what the parallels might be, because it's a basis that is then used for, in the environmental space, for GeoSci-ML, SoilML, and all of these sorts of things. So I was wondering whether there was a parallel between that framework and the indicator framework, or whether there was a critical distinction between them.
Well, actually, I think we haven't really matched this against each other. But if I think maybe the O&M model could replace our just the representation of our basic indicator class, but all the other sections that we have looked at, making the separation between the general indicator, then the object-related indicator, and the reference objects, and then the weaving. That's basically something that would have to be added anyway, and this is not addressed. I mean, O&M has a possibility to say, okay, that observation was made by looking at that feature. So you have that relationship, but that's a very coarse relationship, and does not really go down to the level of individual attributes where you link maybe an observation to a very specific attribute of a specific object.
Okay, thank you. Let me check if there is another question. Yes, there is another one. Sagar Sonone. Sagar, would you like to ask the question, or I can read it?
Yes, if you can hear me.
Yes, sure.
This is Sagar. I'm currently building a smart city model for Middle East, Qatar. So I was just wondering if there are any standards or site suitability techniques which we can derive from the collected data in your models.
In principle, it could be applied. The question is, how do you measure site suitability? If you have rules, or if you are able to express mathematical formulas to give you some indicators for site suitability, then this model could be applied. So, but it really means you need to think about, okay, how do you evaluate site suitability, or at least what are indicators that are important for a planner to decide about site suitability. So maybe not in the end one indicator saying yes or no, but maybe having a set of 20 indicators that the urban planner will always have to have a look at and check. These indicators could be, of course, expressed using this kind of framework.
Okay. Thank you. I see there are no further questions. So thank you once again, Thomas, Tatiana, and Mustafa for presentation and for answering to Peter, Robert, and Sagar.
May I just ask one question? Would this be in principle, I mean, you don't have to answer this now, but would this kind of modeling framework, would this something interesting for TC211, or is that something that is not out of the scope or out of interest for you? I know it's all the question who will be doing it and funding, etc. So there are a lot of things around it, but.
Peter, maybe?
This is Sanki Hong here. If I may, of course, it is very interesting idea, and you know, as you see in my presentation, we always concerned about how we link all these different data models and application schemas and things like that. And we've been looking at all these different ideas, and it's a great way of linking data models. So it is, of course, a very interesting topic to discuss, and we will follow up on that.
Okay, thank you.
Okay, thank you once again to all.